So for fundamental theorem of calculus part 2 is also assume that if f is continuous on the interval from a to b, then if you take the definite integral from a to b of f of x dx, and now what you have here for little f is you take antiderivative of little f and you have capital F of x, and you evaluate capital F of x at a and b. What you get is the formula of capital F of b minus capital F of a, where capital F of x is an antiderivative of little f, or what you say is capital F prime equal to little f. Now, to see the connections between the two branches of calculus, in the first part, you apply derivative operator on integral operator. Now, in the second part, what you do is you apply integral on derivative operator. Now, how would you do that? So you see here you have the definite integral from a to b of f of x dx, right? Now, instead of writing little f of x, by the calculation, by the assumptions that we have here, that capital F is an antiderivative of little f. In other words, what you say is that if you take the derivative of capital F, you get back little f. Okay. Now, instead of writing integral, definite integral of little f, I can actually write the integral from a to b of capital F prime dx. Okay, so I take out the little f, I substitute or replace by capital F prime. It's carried the same meaning, exact same meaning, because F prime, capital F prime equal to little f. So this technically show that you apply the integral on derivative. Okay, so they cancel out and you're left with just capital F. Now you need to evaluate at a and b. And that's what you get, capital F of b minus capital F of a. You follow the idea? So part 1, derivative on integral. Part 2, integral on derivative. So the problems that we need to deal with right now is that we don't know how to find antiderivative yet. Okay, so we need to go through some of the formulas, some of the technique that you might want to use in order to find antiderivative before you can evaluate the antiderivative at a and b. Okay, so that's the topic. That's the next topic I want to cover. That is antiderivative. So in the first part of the course, right, what you do is what? You have a distant function. You take the derivative. You have velocity function. When you take another derivative, you have the second derivative. And at the second derivative, you have something called accelerations. Now, what if you know the acceleration and you want to find what is the velocity after I apply accelerations to the car, right? Or if I start running, I accelerate myself how fast I'm moving. That process is called antiderivative. Given acceleration, you take antiderivative to get back velocity. Now, if I know my velocity, I can determine distant functions. And that process, again, is antiderivative. So here, in the reverse process, you have antiderivative. You take another antiderivative, and you're going to get back the distant functions. Right. When you take the derivative of the function, you get the derivative functions. That's it, right? However, when you take antiderivative of a function, it's not just one antiderivative function. There is something called a general solutions or a family of functions. So what do I mean by that? So let's consider the following example. Consider this equation. So dy dx equal to 3x squared. All right. So in mathematics, this equation, this setup, this particular equation is called a differential equations. And when you have a differential equation, you want to find the representation of the function y in terms of x. Okay. In a way, what you do is, what is the function y such that when you take the derivative of y, you get 3x squared. So that's the questions that we want to address, right? So what function y such that dy dx is equal to 3x squared. All right. Again, at this point, assume that this is the first time you see antiderivative. This is the first time you see differential equations, right? And you have no clue of what function is going to be and what technique that we can apply to find the antiderivative or the solutions of the equations. But you can actually make a guess from your experience in dealing with derivative. Okay. So when you see 3x squared, right, you may go through some of the basic function that you know about, linear functions, quadratic functions, cubic functions, quadratic functions, or polynomial functions in general, because here you have a quadratic function. Right. So it's good to think in that terms, to think about polynomial function in general. And if you make enough guesses, you may arrive at the answer that y equal to x cubed is a solution to this differential equations. Why that is the case? Because when you take the derivative of the function with respect to x, you get back 3x squared. So y equal to x cubed is a solution. It's not the solution, it's a solution. Why that is the case? Because if you think about this, if you choose another function, let's say x cubed plus 1, when you take the derivative of this function, dy dx, you actually also get back 3x squared, right? Because the derivative of x cubed is 3x squared, derivative of 1 is 0, so therefore dy dx is equal to 3x squared. And when you recognize this and you continue working on a different function but in similar form, that is x cubed minus, let's say, 3. Okay. And you recognize that, okay, if I take the derivative of this function, it turns out that dy dx is also equal to 3x squared. And because of this recognitions, we say that, okay, if I don't just have one constant, if I have an arbitrary constant written in the form of y equal to x cubed plus capital C, I have that my dy dx is going to be equal to 3x squared. Okay. And this form that you get right here, y equal to x cubed plus C, is called a general solutions or the general antiderivative of this equations or of the function y. So here in this case, this is called the general solutions or the general antiderivative. And the C that you have in this case, C in this case is called the arbitrary constant. Because at this point, for this setup, we don't know the exact value or we don't know anything about the constancy. It's just that when you take antiderivative of a function, you obtain something called a family of functions. Okay, so that is another terminology that you may want to familiar with. So this is a family of functions. Okay. But there are some cases when let's say you want to throw a ball up in the air, you know the initial acceleration, initial velocity, something like that. When you know the initial conditions of the problem, then you can actually specifically identify the solution or the value of capital C. But in general, when you have a general solution or you want to find the general antiderivative of a function, you just have capital C, which is arbitrary constant. Okay. So let me give you another example here. When you have f of x equal to x squared, and you want to find the general antiderivative, or for short, I just say antiderivative, you're going to get, so this antiderivative. And if you make enough guesses, you're going to see that capital F of x is going to give you 1/3 times x cubed plus a constant c. Why that is the case? Because when you take the derivative of this function, you get back x squared. Okay, and the plus c is there to indicate that this is the general solutions or the general antiderivative, and c again is an arbitrary constant. When you have something like f of x equal to x cubed, and again you want to take antiderivative, you should get capital F of x equal to 1/4 times x to the 4 plus a constant c. All right, and then I'm going to give you one more example here, that is f of x equal to x to the 4th. When you take antiderivative, you get that capital F of x equal to 1/5 times x to the 5th power plus a constant c. Okay. So for these three antiderivatives, you always see the plus c at the end. Okay. Again, to generate the general solutions or the general antiderivative. Okay, so why do I give you this information? Because in general, if you have a power function of the form f of x equal to x to the power n, and you want to take antiderivative, then you have capital F of x has the form of x to the power n plus 1 divided by n plus 1, then plus a constant c, under one assumption that the denominator should not be equal to 0, or you impose the conditions that n is different from -1. Okay, and this one is called the power rule of integrations. So let me give a name for that. This is the power rule of integrations, or of antiderivative for that matter. So with this general information, the general formula, let's try with f of x equal to x to the 10. Right? And if you want to find antiderivative of this function, you have that capital F of x equal to, so I'm going to use the formula here, x to the power n plus 1, that is x to the power 10 plus 1, divided by 10 plus 1, plus a constant c. So the result should be x to the power 11 over 11 plus a constant c. You can write the result in this form, or you can just write the answer in this form, 1 over 11 times x to the 11 plus constant c. It doesn't matter which one that you give for the answer. They are the same. Okay. So that's the power rule of integrations, or power rule of antiderivative. The next topic is that I'm going to give you some general antiderivatives, or some common general antiderivatives that you're going to see throughout your math career, throughout your computer science career, or throughout your physics career. Some common general antiderivative. Here, I'm going to break down into a table of two columns. The left-hand column is going to be the function, and the right-hand column is the general antiderivative. All right, so there's another thing I want to mention here. So instead of keep writing the word antiderivative, I'm going to use a notations, and that notation is called the indefinite integral. Okay, so what do I mean by that? So I want to find the antiderivative of the function a times f of x. Right, so this is a constant multiple, a times f of x, and I want to find the antiderivative of this function. Now, to avoid even saying antiderivative, I'm going to use the notations. That is indefinite integral. I want to integrate this function a times f of x with respect to x. So this indefinite integral meaning that there is no limit of integrations. This information, this is the new terminologies. This sign with dx and no limit of integration is called indefinite integral. Okay. So quickly note here, this is called indefinite integral. And when you take antiderivative or indefinite integral of the function a times f of x, this is a constant multiple. You can pull a out of the integral operations. So you have a times the integral of f of x dx, or whatever f of x is going to be. This is a constant multiple. Now the next one is the integral of a sum and the integral of a difference. Integral of a sum, if you have f of x plus g of x dx. So the integral of a sum is the sum of integrals. So integral of f of x dx add with the integral of g of x dx. And the integral of a difference is difference of integral. Right? So here you get, this is sum and difference rule. The next rule that you may want to know, you already see that earlier, that is the power rule of integrations. You have the indefinite integral of x to the power n dx. Again, we want to impose the conditions that n is different from -1. When that is the case, you have the results to be x to the power n plus 1 divided by n plus 1 plus a constant c. Again, the condition is that n has to be different from -1. So this is the power rule. Now, the next rule should be you want to find the antiderivative of 1 over x dx. So in this problem, right, in this function, you exclude the value n equal to -1. Now, when n equal to -1, you have 1 over x, right? So x to the power of -1, that means 1 over x. Okay. So what is the antiderivative or the indefinite integral of this function, 1 over x? This is going to be ln of absolute value of x plus a constant c. So you have to be careful with the result here. It's not just ln of x, it has to be ln of absolute value of x. Okay. So that's another formula that you may want to know. The next one is the antiderivative of the functions e to the x. So this one should be simple. That is, the antiderivative of e to the x is just e to the x plus a constant c. Now, the antiderivative of some trigonometric functions, antiderivative of sine of x dx is equal to negative cosine of x plus c. So why is negative cosine of x? Because when you take the derivative of this function, you get back sine of x. So that's why you need to include negative sign in front of cosine of x. The next one, the integral of cosine of x dx is equal to positive sine of x plus a constant c. Another one here is integral of secant square x dx. The result should be tangent of x plus a constant c. Now you have the integral of cosecant square x dx. You should get negative cotangent of x plus a constant c. Then I'm going to give you one more formula here. You have the integral of secant x tangent x dx, and it's going to be secant x plus constant c. So these are the formula, the basic integral formula that you may want to know. Okay. And that's what we're going to focus on for the rest of the week, on finding the derivative of some functions. Okay. So let's take a look at some example, right? So the idea of the examples is that can you apply the correct basic integral formula to evaluate some integral? There are something called integral techniques that you're going to learn in Calculus 2, including substitution, integration by substitutions, integration by parts, and integrations involving partial fraction decompositions. And there are some other integral technique that you may or may not see in Calculus 2. But for now, for the rest of the course, I'm going to give you integral of some function. Can you apply this basic information, basic formula to evaluate some integral? Okay, let's take a look at the following example. All right, so I want to find the integral of the form. The integral, so again, this is indefinite integral because you don't have limits of integrations. The integral of 4 times sine of x plus 2 times x to the 4th minus 1 over x squared dx. So you have this integral with 3 terms adding together in the integrand. Okay, so integral of a sum is a sum of integral. Integral of a difference is difference of integrals. So technically you can write the integral of 4 times sine of x dx plus integral of 2 times x to the 4th dx minus the integral from 1 over x squared dx. Right, so notation. In terms of notations, please include this integral sign and dx. Please include the integral sign and dx, and again, include integral sign and dx. Dx to indicate the variable that you want to integrate. Okay, so keep that in mind. So we technically just perform sum and difference rule of integrations. Again, the integral of a sum is sum of integrals. Integral of a difference is difference of integrals. Okay. Now, the next step is just to pull out the constant. Right? So this is a constant multiple rule. So you pull that out of the integral operations. You get 4 times the integral of sine of x dx plus, for this integral, you pull out the 2. You pull the 2 out of the integral operations. You got 2 times the integral of x to the 4th dx Now for the last integral, if you go back to our basic formula, we just wrote down, you don't see anything related to 1 over x squared. You do see the integral of 1 over x, but that is different, right? You don't see anything related to 1 over x squared. However, you know the basic formula for power rule of integrations. So it's good to turn this 1 over x squared into a power function. That is the integral of x to the negative 2 dx. I just use here the constant multiple. Right, so constant multiple rules. And for the last integral, I want to reiterate that I turn the function into a power function, turn 1 over x squared to x to the negative 2, so that I can apply power rule of integrations. All right. Now, if you go back to our basic formula, we see that the antiderivative of psi of x is cosine of x. So you get 4 times negative cosine of x plus 2 times, now x to the 4th, so that's the power function. You apply power rule of integrations. You're going to get x to the 4th plus 1 divided by 4 plus 1 minus x to the negative 2. Again, x to the negative 2 is power functions, so you use power rule of integrations. You get x to the negative 2 plus 1 divided by negative 2 plus 1. And at this point, you may wonder, where is the plus c for every term that you just got here? So you don't have to keep writing plus c plus c plus c. You just need one plus c at the end of your calculations. So here I'm going to do plus c at the end, and that's it. That should be enough for how many indefinite integral you have or how many antiderivatives you have. Okay, just one plus c should be enough. Now at this point, you can simplify your answer. You get negative 4 cosine of x plus 2 times x to the 5th power divided by 5 minus x to the negative 1 divided by negative 1 plus a constant c. Now you turn everything into a positive exponent. That is, this x to the negative 1 should be 1 over x. So here you have negative 4 times cosine of x plus 2 times x to the 5th power divided by 5 plus, you have negative here with negative 1, so negative with negative become positive, plus 1 over x plus a constant c. I'm going to give you another example here. I want to find the antiderivative, or I want to find the indefinite integral of e to the x plus 20 over x dx. Or f1 is equal to negative 2. All right, so this is some new things that occur in our questions. Not only that you need to identify or find the antiderivative or indefinite integral of the function, there's some information here that you need to include in the calculations. When you are given this information, you know this is the initial conditions. When you have an initial conditions, you're going to be able to find the explicit value of capital C, which is the arbitrary constant. All right, so let's first find the antiderivative of the function, then I show you how to find the value of capital C. All right, so for the antiderivative, or the indefinite integral of e to the x plus 20 over x dx, so this is the sum, so the integral of a sum is sum of integral. So you get integral of e to the x dx plus the integral of 20 over x dx. Again, I just perform a sum rule. Right, integral of a sum is sum of integral. So this, I assume this is the first time you see integrals. So that's why I keep writing different rules that I use for each step. Eventually, you're going to drop all of this and just perform the calculations. Okay. Now, the next step is to evaluate the integral. So for the first integral, it's straightforward. The antiderivative or the integral of e to the x is just e to the x. So you get here e to the x plus, for the second integral, you have 20 is a constant multiple, so you can pull that out of the integral operations. You have 20 times the integral of 1 over x dx. Now for 1 over x, you cannot turn this into a power function. There is a specific particular formula for the integral of 1 over x, and that is ln of absolute value of x. So you have e to the x plus 20 times ln of absolute value of x plus just one constant c at the end. So again, I want to say that this is the general solutions on the general antiderivative. Okay. you are given an initial conditions. So this allows us to find the value of c. So consider the function f of x equal to e to the x plus 20 times ln of absolute value of x plus a constant c. We have that f of 1 is equal to -2. So that is when x is equal to 1, the output is equal to -2. So that is e to the first power plus 20 times ln of absolute value of 1 plus a constant c equal to -2. So ln of 1 is equal to 0. So you have this one to be 0. And you're left with just e to the first power plus c equal to -2, or c is equal to -2 minus e. Given the initial conditions, you know the exact value of c. In this case, c is equal to -2 minus e. Then the solutions, then the function becomes f of x equal to e to the x plus 20 times ln of absolute value of x minus 2 minus e is no longer plus c. There is a more specific value for c. That is -2 minus e. This solution has a name. This is called the specific solutions. It's no longer a general solutions. You know the exact value of c, so therefore it's a specific solution.